Okay. Very good morning to all of you. Also, I would like to thank the organizers, management, teachers, students for giving me the opportunity to be here. Information on this knowledge about the application of the differential equation. I'm happy to start my knowledge in the field of numeric analysis, which helps us to solve the differential equation. Yeah. So here I can start my presentation in this stage. So I have given the outline of my talk. Yes. First, I start with the filter is which is related to today's class, which is use the like better recapitulation of your understanding of the course. Okay, and then I slowly with the application of differential equations. We are going to introduce the general application to us, and then like I slowly introduce the research problem in the particular problem. It is also a kind of differential equation again. The thing is, we are going to have some a particular parameter in a different equation. That particular parameter, how it is going to affect your solution of the different equation. That in this case, there are some research work that already done for like last 20 years in this field. Like I have four different problems, similar particular domain, and explain how we are going to approach the problem and get the solution of the different equation. Okay, and then I have some open problem which to be solved. In the two different ways I have given here. One is it is related to similar problem, and how we are going to solve such a problem by using the recent trends of tools like other labels analysis, maybe by using the artificial intelligence and machine learning. Okay, and then the second problem is it's related to human mass problem. It means that we are interested to bring our human researchers to the mass directly to do the research on the mass, like how efficiently we can able to accommodate like our human in the mass. So the research is going on like we are sending the satellite to find the nation of the mass up there. Now like we are looking to send the human to find the research by using the people. Okay, so that I have an interesting problem which is again related to differential equation. Here, essentially a kind of surplusing differential equation we are going to consider. Okay, so I just introduce the problem with time parameters, and then like we have a research tool like I have a more research scholars who are like working under me, and then we have like some collaborators also like these research also I carry out different component team. So that I will only like who are those, and then I will present the answer. Okay, so this is like today's outline of the lecture. With this, I will start the lecture. The first thing is yeah, what I said in the beginning. So we are going to have a quick recapitulation of the course that we are already studying the differential equation. Okay, so hopefully you are very good in the definition of the differential equation, classification of the differential equation, how to solve the differential equation. So that I just try to recall quickly, and then I take the problem or this what we will discuss here. Okay. Yeah. So like can you tell me like what is meaning of differential equation? Like how you can say that differential equation? Can you please read that or like the section to very interesting. give me a working day, like what you understood or what you understanding from the program. It's not just to be a correct answer. I try to make an animation for it. That's why I said, they ask me a beautiful case. Like what is that? What is different thing? Please don't hesitate like really like your mind don't go out like outside your life, right? You can continue that. Good. Deep, yes, different small. Exam. Exam very good. What is exam going? What exam going? What exam going? So I should not ask the next question. Okay. Good. Very good. Now you can calculate variables. The very simple calculation is if the equation contains the derivative. Is a different equation. Always we need to call it algebraic equation. Okay, it's a basic definition, basic understanding of the differential equation. Like we don't want that like the class definition of anything. We just understanding how we are going to approach the company control. Okay. Yes. The thing is here I have written the definition. You can go through that. That is fine. So like the equation contains like one or more than like what derivatives we just call like a differential equation. Okay, I just give you a small example of differential equation. If d by the is equal to 3x plus 3, so like suppose someone said that like two variables, but we need to wait till like what is the mass of the variable. Okay, so here the derivative, the mass of derivative is nothing but a rate of change of different variable with respect to independent variable. That is sense. That is meaning here. Okay, so we should not see like variables. Okay. So if you see like capital in the variable because we are going to have a partial differential equation where we must have like more than one independent variables. Okay, the changes of the different variables with respect to only one different variable that is used to call as ordinary differential equation. And if it is like more than one independent variable involved in a differential equation, then it is called partial differential equation. Okay, that's the classification we have. Yes. Next, what is the solution of the differential equation? What is the solution of the differential equation? Let's go for an example. What is okay, perfect. Okay. So that is a method to solve the differential equation. Good. Any other answers? I'm expecting a find the answer here. E power? Yes. Okay. E power? Okay, E power RS. Good. Yes. Yes. The form of straight line. Good. E power RS in the form of straight line. Any other answer? Okay, so I got to answer quickly. So here, like what is the exponential function? I know like exponential function is easy function. What is the data exponential function? It's just any low. Yes, yes. It's not like about writing function. We are not saying that. Not very easy or full answer. And straight line. Okay, so again, uh, yeah, it may be a straight line, but it's not necessarily a straight line. So your solution may be any way. So it may be a parabola, it may be a curve, any kind of curve itself. Like it may be a cos case curve also it may be. It is not necessarily a straight line. Okay, it's like okay, cos case, it's fine. It's a straight line. It have become answer. That's fine. But my answer is that the solution of the differential equation is nothing but algebraic equation. Whenever you try to solve the differential equation, you are going to get the algebraic equation. I have the solution of this given differential equation, but luckily I have a simple differential equation. I'm going to apply an exact method to solve the differential equation, which is variable circle. It is here is the variable circle method. So a very basic method to solve the differential equation when the function is when you are able to differentiate the variable in the left side and right hand side. Okay. So you are able to make it like separate this variable and like it can keep like only y in the left hand side things that like dy dx can keep in the left hand side. Like all other variables, like we have like another variable like s that you can bring it to the other side. Okay, dx can bring to other side, and we know the concept that integration is a reverse process or different cases reverse process. Okay, so based on idea, I can able to eliminate the derivative t. The derivative I can able to eliminate. So after separating variable y and x left and right side, do the integration, you can able to get the solution, right? Yes, I can able to show the solution here. So like this is my solution, like y equal to x squared plus bx plus c is the integral constant we are applying because like we don't have the region of the integral, so like we supposed to add an arbitrary constant when we do the integration. Okay, you will get this multiplication, right? When you do the when you apply any of the variables according to the after applying this when you do the integration. Is it fine? Yes. So like very generally, I'll tell you, like when you are modeling any physical phenomena which contains the rate of change, obviously it is going to be a differential equation. With the differential equation, we can't able to do any information about the physical phenomena. I have an example I will let you know, but just keep this idea in your mind. Okay? So the differential equation of mathematical modeling will not give information about the model. Okay? So like what we need to do, we need to find the solution of the differential equation so that from the differential equation I can able to get some good information about the physical system. Okay, physical phenomena. Okay, so like for example, I have the algebraic equation. You know that y is a different variable, x is a independent variable. If you want to know the nature of the different variable, we can able to vary the value of x, right? And if something like x equal to 0, I'll get some value. And if something like x equal to 0.1, I'll get some value of y. That means I'm able to get the collection of values that is nothing but information about the physical system. Okay? So like that is the idea, the basic idea. The idea you are in an example problem. I'll just try to like recall the same by using the example problem. Okay. Yeah, this is the thing we already discussed. Like you know what is ordinary and what is differential equation. Yeah, so I will like to fascinating example for such cases. Like these are like properties of differential equation. So like you know what is the degree, right? The highest derivative term and the power of the highest derivative is the power of the differential equation. When the system is like when the equation differential equation is like homogeneous, non-homogeneous, linear, non-linear, unhomogeneous, like we have like four classifications, semi-linear, quasi-linear. Okay, so like, these are the things we already studied. Like I just given the information about such cases. Okay, yes. Can I proceed? Okay. Can I proceed? Yes. So like until now, I just completed what is differential equation. It may be ordinary or partial differential equation. Okay, I just throw an example for the initial and boundary value problem. It is interesting. That is the kind of problem we are going to see in future. Okay. So that's why I have given the definition of such cases. So can you see what is the order of the differential equation? What is the order of the differential equation given here? It's x order differential equation. Good. And is it like constant coefficient, variable coefficient? It's a variable coefficient, right? And the coefficient of the derivatives are like a function of x here. Okay, it's a variable coefficient that may be constant order. You can also like n of x is something one constant and answer. Maybe constant order. That's fine. Okay, so like in addition to the differential equation, like we have differential equation. In addition to the differential equation, I have given some constraint or like some condition I have provided. Okay. So like here like the conditions are like n condition I have considered. The reason is my consider the differential equation is n order differential equation. Okay, if it is n order differential equation, you must have at least n condition or constraint to solve the differential equation. Okay, yeah, that is the idea. So here I have put like n values. Like so you able to see this. So this is my first value. The solution the different variable defined at x naught, the values alpha naught. It's alpha basically constant values. Okay. Similarly, the derivative of the solution like y dash of x naught, the same point I have given. It is important. The y dash of x naught is given. Okay, the same point we have given y double dash, y double dash, and so on. I can go this y n minus 1. Okay, the solution and derivative is given. And yes, the single point that is x naught. Since the solution of its derivative given as a single point, it is used to call the initial value. If the solution is solution of its derivative defined only at the initial value x equal to x naught, so that's why this combination, like differential equation and the constraint, is used to call the initial value problem. Are you able to follow? Since it is defined only at x equal to x naught, y at its derivative, it is called initial value problem. Along with the differential equation, we have some constraint or conditions here. Okay. So now I am going to extend the definition to the boundary value problem. If it is given like at one point, it is initial. If you define at two different points, it is boundary. Okay. I will show you what is boundary value problem. Before that, it is very important. When you are dealing the problem with the numeric analysis, we must adapt that like the solution of the differential equation exists and the solution should be unique. That is necessary, right? If I am trying to find some value, that should be a only value. If I am solving the problem, getting some value, if I am getting some the same problem, is getting a different value, the third person getting a different value, it does not have any sense. Okay? It does not meaningful. Okay? It should be unique value. So like whenever you are trying to solve the problem uniquely, the first thing is we need to check this theorem. It's a theorem actually. So we need to check or we need to show that consider initial and boundary value problem should have the solution. Basically, it should have a solution, and that solution should be unique. Okay. So like this is a condition we have like to check the condition. So basically, then the coefficients, like all the a and r should be not equal to 0, should be continuous, and the right hand side of the construction should be continuous here. And the first coefficient like a n of x is should not be equal to 0. The reason is if the a n of x is 0, the order of the differential equation is reduced, right? Right? So then you won't get the exact solution. Like you won't get the unique solution. Okay, so like this here like a n of x should be not equal to 0. Okay, so consider interval. If it is a linear interval, this is the condition you need to satisfy. Okay, if it's satisfied, then I am able to say that x is your point like x equal to x naught. In the interval, like maybe you can take 0 to 1 is the interval. So it's always within the 0 interval. And then like any point in the interval, assume that the point is 0.1. Okay, so if you take an x naught equal to 0.1, so and if you substitute the values in the solution like y of x, the solution may exist. If the solution exists, then obviously here is solution is unique. That is the case we have. Okay. And it's based on my assumption what I have given the first slide. Okay. So assume that we have the solution and solution is unique for the constant initial value problem. Okay. Yeah. So next I'll move the boundary value problem. Oh, I'm sorry. I have an example for such a case. So here I need to move quickly. So I have the differential equation. This differential equation given in the interval, it means that complete x plane, the complete x axis, like minus into plus infinity is defined, and some conditions are given to us. Y of y equal to 0, y dash derivative of y equal to 2, and y double dash at y equal to minus 1. Can you tell me, is it the initial value problem? Is it initial value problem or boundary value problem? I didn't introduce the boundary value problem, obviously to be initial value problem, right? Like another case, you need to check the given constraint. So here the constraint is, or the function is, the solution function is defined only at a particular point, like x equal to pi, right? So y is defined at pi, y dash is defined at pi, and y double dash also defined at only pi. Okay, so that's why since I have given the differential equation, we have three conditions, and those three conditions are defined only at x equal to pi. Okay, so then it's used to call as initial value problem. I can able to solve this initial value problem. So luckily, I have considered, it is given that the family of the solution is given to me. Okay, I don't want to use like general what is it? Complement function, particular those things like I want to do. Like you are good in that, I hope. So I just taking the it's a family solution here directly here. Okay. The only thing is it is not a particular solution. It is a kind of a general solution. Am I right? Because the constants are like unknown here. We have C1, C2, C3 are the constants. All those three constants are unknown. Even if you substitute like some value for x, value of x you can substitute like here cos x and sin x, but still we have some unknowns. Okay, those unknowns we need to solve. For solving such a unknowns, it is given to us. The initial value of given to us. Okay, I will show you how we are going to solve such unknowns. Since I have like general solution, so to find the unknowns in the general solution, I can take like this. Okay, so this is my first condition: y of I equal to 0. So let's substitute this condition in my family of solutions. Let's substitute like x equal to 0. So we don't have variable x here. Here we have variable x. What is cos by cos 180? What is cos 180? Minus 1. Good. So on sin 180. 0. Okay, so like cos 180 is minus 1, we have like minus C2, and sin like sin pi is 0, then third term is like completely vanished. Okay, so like you will get like C1 minus C2, your right hand side is 0. You get an equation C1 minus C2 equal to 0. Okay, similarly, I can able to get the other initial conditions, but those are derivatives. Okay, first find the first derivative of the given equation to y of x. So it will be like y dash of x with respect to x and 3, and then you can use the condition like the y dash of x, you can substitute like x equal to 5 and y dash of y equal to 5 equal to 2. You can substitute, you will get the equation C equal to minus 2. Is it fine? And it proceed. So like I have like one more initial condition, that is second derivative. Like you need to find the second derivative of the family of solution, and so you supposed to like substitute this initial condition. We will get equal like C1 equal to minus 1. Okay? So for the reverse line, we have to solve like 5. I have a value for C1 directly, C3 also is direct, but I need to get like value of C2 alone. Substitute C1 in the first equation, so that I am able to apply the C2. Okay, since I have like all the values C1, C2, and C3, you can substitute the original solution. So you can replace here, you will get a particular solution here. Okay, I will show you the complete solution here. So y of x equal to minus 1 minus cos x minus 2 sin x. Okay. So now you can able to find the different value of the function by substituting the value, because it's a particular solution now. Earlier it was some arbitrary constant we had. Now we have a particular solution. So with this solution of the differential equation, you can able to get some information about the system of equations. About your differential equation. It's not a system; it's a single equation. Is it fine? Can I proceed? Yeah. So then I'll go for the boundary value problem. Like here the case is I have considered the second order differential equation, and this like since it's a second order differential equation, at least we need like two conditions. Here I have considered in such a way y of x naught equal to alpha and y of x n equal to beta. Look at here, the constraint is different. The two different two different values. One is at x naught. Y of x naught is defined, and this is on other one like y of x n is defined, that is d1. It is not the same one. The condition is given in the two different points. Okay, the x naught may be a starting point, and y naught may be x n may be your end point of your solution. Okay, in such case, I will say that if it is a boundary value problem. Is it fine? The equation differential may be defined in the interval, in the open interval x naught to x n. Okay, yes. And so when you are trying to solve the boundary value problem, we can expect like three kinds of solution. We may have the solution or no solution. We may have the infinitely many solution, or we may have the unique solution. Okay, so I have given an example for such cases. Yeah. So here I have considered a second order differential equation again, and it is different in the interval minus infinity to plus infinity to. So like directly I have considered a family of solutions here. Okay, the question is, I'm going to take like two random boundary conditions, and I will check that whether it satisfies the given family of the differential equation. Yeah. So like first case is this is initial condition or boundary condition? Is it initial or boundary condition? It's a boundary condition. Okay, the y is defined in two different points. The points are -1 and +1. Okay, so obviously the -1 +1 will arise in the interval -2 plus infinity. Okay, I am able to consider this is my boundary condition for given differential equation. Now I am going to repeat the same idea. I am going to pass like this initial sorry this initial this is like this my initial condition, this is my terminal condition in my family of the curve. Okay, and the consider y equal to y of minus equal to 0. Substitute the family of curve. It's just a polynomial only. When substitute, you get the equation with c1 plus c2 equal to -3. When you try for the like terminal condition, I'm going to get like another equation c1 plus c2 equal to +1. Will I able to solve this system of equations? Now I need the constant value, right? Like C1, C2 are unknown here. I need to get the constant value. Will I able to solve this system of equation? System of will I able to solve this equation? Will I able to solve this equation? If there wants to be an answer. So after you solve the equation, we'll find some common value of transfer like one constant will find the other one, right? There are two unknowns we have, like C1, C2 are the unknowns, and like we to find those two unknowns, obviously we have the two equations. Okay? If two equations are two unknowns, we must get the unique solution, right? I can get a unique solution, but unfortunately, look at the equation carefully. These two are the, like if you draw these two lines on the plane, on the xy plane, it's going to be a parallel line. It never meets anywhere. If it is intersect at a point, that should be a solution of close to a straight line. Okay, but unfortunately, we are going to get a parallel line. We should understand the geometrical meaning, even if you try to cancel. You can take the second equation multiply minus 20, you get minus 0, C1 minus C2 equal to what you get. So like if you cancel it, both C1 and C2 will get cancelled. We won't get a solution, okay? The reason is if these two are a straight line on the plane and those two straight lines are parallel lines. With the parallel line, we won't get a solution. So like for this consider boundary condition, we won't get any solution. It is unfortunate. Okay? I'll go for like different boundary condition. Again, it's a boundary condition between the two different points x equal to 0 and x equal to 1. Okay, fine. So like now I will substitute like these two boundary conditions in my like any family of curve. I suppose to get the equation like this. Like look at here. We are very unfortunate. The first equation like it's not equation basically. 0 is not equal to like, 3 actually. Okay. And look at the second one. Like we can't like, consider this. When we go for second one, we will get C1 plus C2 equal to -3. It means I have two unknowns, but we have only one equation. We are not able to solve the different equation. If I want to solve the different equation, I must go for assumption for any like either C1 or C2. Like nothing like C1 equal to something like alpha, then like with the value of C2 in terms of alpha again. Okay. So the reason is in the geometrical view, we are going to have like only one straight line. Okay. So in such a therefore intersecting point, we won't get any solution for such a case, but I can able to get infinitely many solutions by assuming the value for any one of the constant C1, either C1 or C2. Okay. So like this case, like again, I'm not happy with the solution. Okay. So now whenever we are solving the problem, we are always interested to get the unique solution. Okay. Yes, we need to go for some different boundary conditions, but I didn't give any boundary conditions to the unique solution. Okay, so like still we can able to like do the analysis to find the such a kind of boundary condition which is the interval minus into less infinity. Okay, yes. So yeah. So with that, I know like we are good with the differential equation and we know like what is the meaning of infinite boundary value term. Am I right? Yes. It's like. You can understand that like what is the difference between it must have a rate of killing or a physical problem which has a one variable is called the other variable is called the differential equation. Such a kind of physical problem, to understand such kind of physical problem, to get a knowledge about such a kind of physical problem, we are going to have some applications. So these are like some list of applications I have provided. I can't discuss like some applications in detail, but I think so like we can't able to like look into much about the research problem. So like I just give this. So these are like applications we have. Like even like you can take a first example, spread of the disease. We know that the reason corona period. Like when I used to get a news like there is a like 30 people affected by corona and ARCOT, something like used to be right. That day by day that the various things will change. Okay, there are two cases. One must be like some people will get used of the coronavirus. In other cases, like some new cases will arise. Okay, so they will find those and they will directly then and they will the information about the spreaders of the corona in particular this week in particular day. Okay, so like this, I able to find like really like good, very good number of data like for 1 week, for 1 month, for 1 year. I can able to predict what should be an expected spread of coronavirus like after 2 months. I can able to say. Okay, so for the we need to have a good number of data, or otherwise we need to model such a physical problem into the mathematical equation. If you model such an equation, what should be an answer? What should be an answer of your equation? Either differential or algebraic equation. Did you understand that like here the time is involved in right? I will just to find the status of the disease after 2 months, after 3 months, after 4 months. Like then the time is involved in so like your the status of disease will change with respect to the time period. Okay, so there will be if you model such a physical problem in the form of mathematical equation or mathematical modeling, you suppose get a different equation obviously. Okay, likewise, if you carry out like any problem, population growth, chemical reaction, like water population, air population, air population, it's going to be involved with the time period, so that you get a different equation of the form. Okay. Yes. So this is an example I'm going to discuss. Maybe like you already like mentioned this example, but my intention is like how we are going to model this into different equations. How we are going to get the information about the physical system. That is the intention here. Okay. So if you are like when you know the case also, like, just follow me. I just going to like a few points here. Here the case I'm going to take yes. So, like, what is the picture you can see here? It's a coffee. Why not it's tea also? But it's never been full coffee or cold tea. But it's some hot coffee or tea. Okay, so like as you are like I can consider the given is hot coffee. Okay, the thing is I want to find the temperature of the hot coffee. Apply find the temperature here. Apply find the temperature. Right? It is fine. I have like if I like the thermograph is given to us, I don't want to spend time to find such a model and such a solution here. Okay, I can able to like with my thermometer, I can able to find the exact temperature. Alright? Okay. It is useful. It is a laboratory or institute. Okay, I'll tell you what is the advantage of modeling here. Okay, like if you take this such a problem, like I have a constraint here and the thermometer is not given to you. Okay, now Like what is the other option? I have a stick finger, I can dip my finger, I can feel the heat, but I am not able to see the temperature here. Okay, so that is also unfortunate. With the other option like become any equipment. Okay, like these are like cases we have to find the temperature of any hot object or hot water or coffee. Okay, so like so in such case like what I will do, I am going to use like again like as he said, it is a law of cooling. Okay, so like this kind of interesting law we have to find the temperature. So like if I want to find the temperature of the coffee, so like I can able to use the law that is like rate of change of temperature of an object is directly proportional to the temperature of the object and the temperature of the surrounding. It is my law. Okay, so now I am going to apply this physical problem into this law. Okay, yes, like I need to define the objects here. What I do, I take I take this picture. I am comfortable with this picture. Look at here. I am going I have an object. The object is coffee here. I am going to define my temperature of the object is with some variable to be like T naught. I am assuming here. Okay. So temperature of object is suffix and given O. It means an object is sensitive. Okay. And you is what is the temperature of surrounding means that right. The temperature of surrounding is like our room temperature. Right now, like our room temperature is like this, right? Because we have the cooler. Okay. If you like outside, like you know, like you have 34, 33 Celsius. Okay. So that is the surrounding temperature we need to consider. Okay. So like when you apply the different, like I just fix my object, I'm going to take my Newton's law of cooling. So like if I use the Newton's law of cooling, like, the object is T naught, the rate of change of temperature of the object. This is the rate of change, right? T naught by Tt is the rate of change of T naught with respect to T. Am I right? So that is rate of change. It's directly proportional to the difference between the temperature of the object and the temperature of the surrounding. Different between subtract of those two variables. Okay? So this is my Newton's law of cooling for my physical problem. My physical problem I just considered. Okay. So like of course I got some proportionality. I didn't get the equation. Is it equation? It is not equation. What we have obtained is not equation. It is a proportionality we obtained here. Okay. The thing is, we want to get the equations of order we need to introduce at constant. Okay. The constant is like positive constant, negative constant. There is no resistance in this. But in the Newton's law of giving, like Newton's law of giving, the law of cooling is giving us if the temperature of the object is reducing. Like if the temperature of object is like higher than the room temperature, not like the temperature is reducing, okay? And the temperature of the object is like lesser than the room temperature, we need to take the like positive value. It will be like if the temperature of the object is higher from the decreasing to the room temperature, but temperature, we need to take a negative constant. It is like decreasing from the room temperature, we need to take the positive constant. Okay, so like by temperature of the coffee is obviously like hotter than the surrounding temperature, so we will take like otherwise it will go. Okay, yes. So in such case, like I need to take the negative constant, I can take my constant is some minus k. So we are taking like minus k. Right, maybe here maybe like very arbitrary constant here. Here I can this is yeah, after introducing thermal constant like minus k, that proportionality becomes an equation, and the equation actually is differential equation. Am I right? Okay. So I have a differential equation like yes, I have a coffee. I want to find the temperature of the coffee. I apply the Newton's law of cooling. When I able to give the temperature of the coffee now, and then when I able to give the temperature of the coffee now. Yes or no? We need to open. Yes, they can be done. Will I able to get the information level or will I able to get the temperature of coffee with this equation? Yes. Any answer? I'm saying like no. I'm standing with no. How can I follow this? I'm standing in the opposite corner. No one. Please believe me. This is true only. Just follow. That's the thing. And it is not possible. Like, how can you say that estimate of opportunity? That is the information we are given that dealing, right? You people that after different sequences, I thought we have to key information. Another model. The model is the number of different sequences. Sometimes you are able to give any information. I will tell you, when you solve the different equation, what should be your answer? What should be your answer? It's an algebraic equation. That is the definition I have given. That's the purpose I have introduced that first. Okay. So when you solve the differential equation, it's going to be an algebraic equation. Okay. So assuming you have algebraic equation, you have like y of x, right? Just look for like the first line. You have like y of x, you can solve the value of x and get the value of y. Okay. Just come there. I'm not going to solve the problem. So like you are familiar with that. Fine. So again, like it's a simple case. The difference is a very simple case. We are able to variable. I can able to obtain the variable separate method. I'm going to separate t naught the right hand side and the other left hand side. And like this ts is not a constant here. Sorry, not a variable here. It's a root temperature. It's going to be a constant value. Okay. And like only two variable like t naught is a variable and spot is a variable here. I just separate as a variable. Of course, I am able to take the integration on both sides. So when you take the integration on both sides, left side you will log off the denominator and right side you will get minus t plus c. What is our ultimate here? What is our ultimate here? What should be our ultimate? What should be our ultimate here? Why I am taking this? Basically, why I like you are like dealing this problem? Good. Find the temperature of the coffee. The big temperature of coffee is given as T naught, right? I'll separate T naught to the left hand side, or on the will be the right hand side that I'm going to do. So like and now something to rewrite the equation, I'm going to do some mathematical logic without doing the mathematical logic here. Yes, I will just take exponential on both sides to the normal perimeter. I will get exponential of something like this, like some of like matter will do. Okay, so if you're able to relate it exponential e equal a e for b that I have done in here, and then like you know t naught will be equal to t is plus t1 e1 minus at. Okay, so this is my algebraic equation I am able to say, and here the t naught is your different variable. Am I right? T naught is different variable, and the T naught will change with respect to what? With respect to the independent variable time. Am I right? With respect to the independent variable time it will change. So if I give like time t equal to 2 minutes, another hot coffee with me, like I want to find the temperature of hot coffee after 2 minutes. Like I can able to take like t equal to 1 t equal to 2. Am I right? I can able to take t equal to 2. I can able to subtract. So I can able to get after t naught. T naught is again like temperature of the coffee, right? That I can able to do. If I want like 500, I want to find the temperature of the coffee like in 1 minute. So I want to prepare like another coffee. I will wait for 1 minute. So I have to repeat this. With physical or experiment, this is not possible. Okay? Or like possible that it is like complicated one, let's say. Okay? In such a case, if you are able to model such a physical problem in the form of a mathematical equation, we can able to find any time period. Time will be like 30 seconds, time will be like after 40 seconds, 1 minute, 2 minutes, like after 3 minutes, it will come to the room temperature. Okay? Yes. So that I can able to like get it only with the help of algebraic equation, not from the differential equation. Are you able to follow me now? Is it fine? Yes. But unfortunately, no one agrees. So like finally, I'm going to get an equation like this. When I substitute the t value, time value, I can able to get the solution. Temperature of the object, not necessarily a copy, not like it may be any object. In the industry, they can able to take this model now, like or they can able to take the Newton's law, they can able to find the temperature of the object. Okay, fine. So and one more thing, like here, like what are known to us in this algebraic equation, it is like all the parameters are like known to us. Uh, can I have one by one at least? If Ts is known to us, good. It's a room temperature. I can able to measure like generally like in ARCOT I can able to say it's 36 degrees Celsius. Okay, like roughly I can able to say at least. Okay, and here like K, this K is known to us. Constant value it must be given to us. Okay, so like it's the kernel temperature is given to us, and T is the time we are going to pass. Okay, we are going to pass that I can able to get it, and there is one another unknown here that is C1. C1 is the unknown. It's like arbitrary constant. We are doing the integration. We are getting the arbitrary constant. Okay, like to find that arbitrary constant. Now I go back to my previous definition. I need to know the initial condition. Am I right? If I am able to get the initial condition, I go back here. So I have some equation like this. If I have an equation something like this, yeah. So if I have some equation something like this, like you have three unknowns. If the initial or boundary condition is given to us, I can able to get the like C1, C2 value. Okay. But unfortunately, this problem we don't have. But to identify the unknowns, we must have some initial condition. If we have initial condition, I can able to eliminate the arbitrary constant. Okay, so that like you will get a complete model to solve the problem. Are you happy up to now? Yes. Can we proceed? Yes, I have discussed like different equations, integral value problem, boundary value problem, and application of different equations. Okay, so that we must know where we are using and why we are using. Okay, so I just completed. Okay, so with this like a small introduction. Last time I was using that's why I misunderstood. Yes, it's a population. When you want to find the population, it's about the population. Population is like only the number. It may be it may be a word which is anything. Okay. If you are able to find the population, you have to use the other kind of model, that is the population growth. It's another model, NC model, to find the population. Yes, like if I use that law, I can able to get the proportional again like this. With that, I can able to get the different equations, and finally, I can get the algebraic equation by taking the time here. Sorry, by taking the different time period, I can able to find the population of anything. Okay. Yes, now I am going to take the research problem. Okay. Actually, I don't have the board here. In such case, I will show you the problem first and I will go cover that introduction. I tell you what is the difference here first. Yeah, please look at it carefully. Like, what is the nature of the equation given to us? Is it different equation, integral problem, biological problem, or something else? Initial value problem. Good. Any answer? Is it given? Okay, fine. Yes, it's already given the PPT itself. It's the initial value problem. Will you able to see any difference in this initial value problem? Good. Can you like find what is the difference in the initial value problem? Can you find what is the difference here? Yes. order one. Yeah, we come. Like order one, we have the only equipment. In order two, we have the same equipment. First order. First order linear differential equation. Of course, I agree with you. It's a linear first order differential equation. My question is, what is the difference between our useful integral value problem and this? That is a major difference of singular pedagogy problem and integral value problem. Will you able to see there is something along with your body glass? So what is that? It's a constant value. Anyway, like obviously it is a constant value, but I am going to call it as a perturbation parameter. Okay, I am going to restrict my value of epsilon. It means the larger value, if the epsilon is like greater than 1 or any larger value, it is a useful differential equation. Useful integral value problem. But here I am going to consider this epsilon is going to be like very small. Okay. So when you solve the kind of differential equation, it's going to create a non-uniformity condition, or it's going to give you the oscillation solution. Generally, if you solve the differential equation, it's going to be some smooth curve. Maybe any vector, some smooth curve is going to be a solution. But here, if you solve this initial value problem and consider your epsilon is 0 less than 1 less than 1, or like very less than 1 or very small value. In such a case, it's going to be create a layer here. Let me know layer in the sense like these are kind of smooth solution, something like this. In the initial point, you are going to get like sudden peak, and then it's going to be smooth. Okay, that is the difference we have. We have a sudden peak rate. We are going to fail to solve such a sudden peak by using a classical method or usual numerical. We have a n number of numerical methods. If you use such a classical numerical method, that won't resolve the sudden peak here. That peak is used to call as boundary layer. Okay, so like this is carry on like for past 40 years, this is going on. Like we are trying to consider like different layers of the problem and trying to resolve the boundary layer. I tell you like what is boundary layer and what is the application of usefulness of the boundary layer. Okay. Yes. Now I come back to my yeah. So like this case, like you know, like what is difference between the differential equation and like we have like an extra parameter epsilon, and it's going to be with this nature. And if you have the parameter with this nature, then your differential equation used to call a singularly perturbed differential equation. Okay, and I'll let you know why we are having that sudden peak. I'll let you know. Okay. So when you are trying to check the like when you are going to take the epsilon equal to 0, what will happen? When you take like epsilon equal to 0 in the previous problem, what will happen? The derivative values, right? If you multiply 0 with the first derivative, that term will go out. Like that term will be 0 or values. You will get it only y of x plus something will get here. Okay? So it means that like we are going to lose like one or more boundary condition. Okay? It means that there exists a non-uniformity occurs in the neighborhood of the boundary or initial point. Okay, so here the non-uniformity occurs, but that's not for our problem or we have considered. Due to non-uniformity only, we are going to get the sudden changes in the solution. Okay, so like yeah, that's the thing. So like actually this experiment is done by Frank and his German mathematics. So we have done like both the way. We have done the experiment, the experiment fluid, like crystal fluid, like any fluid, like crystal fluid, like crystal fluid. It's passing through like crystal fluid, like we have friction, like you can take honey, something. Okay, it's passing through the any tube or any medium is going to pass through the medium. He's trying to do the try to analyze such a physical problem in both a way. Only like extremely is done, the other way we have done some mathematically. Okay, so now we obtain two different solutions. If the solutions are like, when you always say, if you get two different solutions, the experiment and then in the mathematically, it is not going to be same way. Some difference we have. Okay, so the difference is nothing but boundary layer. When the same distance will passing through the medium, in the middle of that medium, it will like cube or wall. In the middle of the medium, the, the flow will be a useful flow or useful flow will come. But on the boundary, due to the friction, the velocity of the fluid flow will be less. Am I right? Because there is a friction we have, it will like when it is passing through the boundary of the medium or solid surface, it will be less velocity compared to the velocity in the middle of the tube. Okay, so like here we have that slow velocity rate. The velocity happening into the boundary range. Here is one example. He identified the 95. Yeah, 95. When you do the experiment. Okay, like with the help of this boundary layer, we have like very huge number of applications nowadays. Okay, so like before that, I'll just give you like an example. Okay, I won't show it. It's not. Both stories like a creative story. Okay. Yes. So like we have the like cylinder, gas cylinder, right? Okay. So like we are like if you get a new gas cylinder, it's like completely full. Like what should be a pressure in the cylinder? Is this or high? Less or high? Yes or no? It should be like very high. Okay. This is equal to answer. So like this should be like very high. Okay. So when the pressure is we have a law. When the pressure is very high, we are going to have the less velocity. When the pressure is very low, that the pressure is very high. That is a like law we have. Okay. So like we are not going to connect with the stove. We are going to by this way we are going to open the like cylinder. In such as what will happen? It will blast, right? Along with the blast, the cylinder will go out, right? The reason is inside the cylinder we have the high pressure. When you suddenly open the pressure, it will move to the low pressure area, and such a case we are going to have high velocity. Due to that, the cylinder will go out. Okay, so that is the reason, the physical reason. The cylinder will go out here. Okay, the same logic like, the people are using the lifting of the aeroplane. You know, like the plane is on the floor. Like when you move like very fastly, it's like getting lift and it's flowing right, and it's like after a certain level it's going to be like when the flow flat. Okay, so the thing is like how it is floating. That is the matter. Okay, that floating is happened due to the boundary layer. Okay, in such a way they have prepared the wing. Help of only the wing. Okay, I'm talking about only the wing. We have like different kind of aircraft. Okay, like military they have to say some different. They don't want to go for long way to run and like this. Okay, so like this is like very aircraft to aircraft. Here I am going to take like computers for aeroplane. Okay, so like here in such a case, like I have just taken the like the cross section of the wing of the plane. Assume that like another plane. Okay, assume that another plane I have like two wings on both sides. Okay, like I'm taking like the cross section. Okay, I'm taking only the cross section. So like the thing is, when the plane is like want to lift, like it will come to the track and it will run for more than 250 kilometers. Okay, you can able to understand like it's going to take the opposite direction of air. Like your air will be like very high velocity will come right towards your aeroplane or wing. Okay, so like assume that this is a wing. So like we have like a shape like this. Okay, you can able to see the difference in the shape. In the bottom of the shape is like length is less compared to the top right. In such a way they have prepared the wing. Okay, so here the length of the top of the wing is like lengthier, and like the bottom length is like comparatively lesser than that. Okay, it is there is a reason, and it is like very efficient design they made. I'll let you know why. When the flow is coming like high speed, like what will happen? So that the air will go up and down like this. Like we have like up, this the streamline. We have given the streamline of the air. It will go in this way in the upper, like above the wing and below the wing also. Then we have the air flow. Okay, so like assume that air also like kind of slightly viscous fluid. Okay, so like it means that it does not have any velocity on the surface. If you have the medium or tube on the surface, like the velocity is very less. Okay, the velocity is very less, and like the middle the velocity is like very high. That's why we have the very good flow in the middle of the tube compared to the boundary of the tube. Okay, the same idea. So here we don't. So we have like a low velocity on the boundary, and that's why we have like zero boundary layer. Slowly the boundary layer size is increasing because here we are going to have the uh, like boundary layer up together. Yellow is completely like boundary layer. Okay. And second thing is like we want to lift the airport, right? Okay. So like here in the top we are going to have like very high velocity compared to the bottom. Okay. The thing is we have like we can take like in the just before the we get to medium. Like if you think about the movement of the medium due to the due to the running the airplane. So here, this will come like this. This will come like this. What I'm saying is that medium will come like in the top of the wing, it's going to be very fast, and bottom will be it's going to be like slower. Okay. So when you move the same like wing in such a way like in the little down, it's again you're going to have very good velocity in the out. When your velocity like higher in the higher in the top, my pressure is like going to be lower. Am I right? I'm saying like this might be my velocity of the flow, the airflow is like very high because initially it was the wing is like this. Now it bends the wing like this. So we are going to have like lengthy top. Due to the lengthy top, the velocity of the air will be like very high here. In such a case, like the pressure of the like the pressure above the wing is like lesser compared to the below. Okay, it means that from high pressure to low pressure, the air will try to move from high pressure to low pressure. Okay, that's why like when you go for like 240 kilometers faster, and you are moving the wing to it is down the back side, here like the air will go from the low pressure, high pressure to low pressure. That the lifting is happening here. Are able to follow? It is like because of the same principle only. Okay? Yeah. So like I'm like in this experience in this physical problem, we are going to get the boundary length in such a way like this. Okay? So it's like a very lengthy topic to discuss. This assumes that there will be some boundary layer on the link in this experiment. Okay, like this in the tube also. Okay. So like these are like some fascinating examples for the boundary layers. Okay. Yes, like these are like some starting from the behavior of this test. These are like some more examples. The problem under is like different domains, not only the fluid mechanics, not only the aircraft thing. So like these are like several applications, several applications for the signal protection problem, and it was deal with different papers. So those by highlighting those papers, I have given the application of the signal protection different stages. Okay, just keep it like there are some applications. That's relevant to the protection problem. Like we have like two types of signal protection problem. Here I have one like differential standard differential equation. When you take epsilon equal to 0, this is when you take epsilon equal to 0, this term will vanish, right? Then we get only the first derivative term. Okay? If such a kind of problem, like if it is the case, the problem is used to call as convection diffusion problem. The other case, when you take epsilon equal to 0, the order of the differential equation is reduced by 2 instead of 1. That is called convection diffusion problem. Okay? So this is an example of convection diffusion problem, and this is an example of reaction diffusion problem. Okay? So now, let's slowly I'll move to the method to solve the single predictable problem. Okay, like at least we have really clarity about the single predictable problem or application of single predictable problem, right? You may have an extra epsilon differential equation. Okay. So now, like as I said at the beginning, when you find the solution of the single predictable problem, you are going to have a current P. Okay. To resolve that P, like what we do is we need to modify our numerical method. Okay, generally, like our classical methods. Okay, classical method will not like help us to solve the problem. Like even if you take the variable circle method, it should not help us to solve the kind of problem. Okay, if I move to the partial differential, 2D partial differential, that is not possible by using the classical method. Sometimes Asmwc method also will not help us to solve the such a kind of problem. Okay, now we have only after this we need to go for the numerical solution. Okay, and we have this advantage in the numerical solution. The thing is when you are finding the exact solution, that will be only solution of the differential equation, right? But in the numerical method, you can get the solution, but the solution is approximate solution. Okay, it may be close to the exact solution, but still it must have some error. Okay, so finally we have like nowadays we have like very good supercomputer with us, and secondly we have very good vector with us with the help of spectrometer and able to solve the problem as better. Okay, industry people are using such a better method. Like for example, example is a finite difference method. We go for finite element method or virtual element method. So those methods will give like better accuracy than other numerical methods. Or it can be very close to the exact solution. Okay. So like here, as I said, like my classical method not help us. In such case, what I will do, I will go for some non-classical method. Generally, in literature, in last 20 years literature, mostly we go with the finite difference method and finite element method. Okay. So I am going to follow the like one is to finite difference method. One is called fitter operator method, and another is fitter mesh method. Okay. The thing is, like fitter operator method, like it is not that much technical method. Okay. So what I will do, we have epsilon in the derivative, right? Like due to the epsilon, we are getting a boundary layer. Am I right? Due to the epsilon, we are getting a boundary layer. To resolve as a boundary layer, what I will do, I am going to use a parameter that is called like sigma. Okay? The sigma is a small parameter which helps us to resolve the boundary layer. The peak will resolve. Okay? The boundary layer will be detected very properly. Okay? By the help of the sigma. The sigma can be determined again by using a given problem. Okay? By using a given problem, I can able to get the sigma, and if you are solving the given problem, when you use numerical method, infuse the sigma, like you feel like that's why into sigma into beta, you can solve the problem, you are able to get some better solution. Okay, okay, I didn't do any modification in my mesh, I didn't do any modification in the display execution. Okay, so I just introduce an additional formula in my solution. With the help of the additional formula, I am going to resolve the boundary layer. That is my first method, is an operator method. But as compared to that, I can able to say like the five methods method is very good here. Okay. The thing is, actually I need the board to discuss. Maybe I have some picture in the future. Later I will explain. Yes. So like listen. So this is my solution summary. The solution summary is start from 0 to 1. Okay. The thing is, like assume that my boundary layer is close to this layer. It means like just follow my laser. My solution will be something like this and then flow like this. It will come. Okay. So like we have this peak here, right? So this peak we are going to find. Okay. This is my solution domain. So like the peak will be in this interval. The peak we need to be determined here. Okay. So when you go for like a classical method, so what we used to do, throughout this domain, we will introduce like n mesh points. Throughout the domain 0 to 1, we are going to split into n mesh points. Like assume that you have like this 8 points. So I will have the points like this. So like this is the domain. So I will introduce like 8 points like point 1, 2, 3, 4, 5, 6, 7, 8. Like 8 can be here. Okay. 8 mesh point I will create. If it is a smooth curve, it is fine. You can able to get that. That 8 point is enough to follow your in this place I have like a peak like this. Okay, so in such case, what I will do, I am going to divide my region into two intervals. Okay, like I am going to divide my region into two intervals. So this is my first interval. The interval is like very small. The reason is I am going to reduce as much as many points only in this interval. So if we have like 8 points, I will take the entire 2 points. 8 by 2 is 4. In this small interval, I am going to introduce 4 points. Okay, so that like it will appear on the solution like you will get like little smooth solution. Okay, if we assume that we have like 64 point, like 130 point, like 64 point, we will give like only in this small interval. The rest of the 64 point we will give the other second of the interval. Okay, tell me what's the reason? What is the reason I am going to restrict like this? The reason is I have a peak solution. To resolve such a peak solution, I am trying this. Okay, I'm trying to reduce as many as this point only on the boundary layer. Okay, the second thing is how I can able to identify this point. This point is used to call this transition point. The transition point will help us to divide the boundary layer, the layer region and regular region. This is layer region, and rest of things are like regular region. The regular region is very smooth. The layer region is now the boundary layer. Okay, so like since I have a layer, like I have like peak layer, I can use like much point to find the peak layer, and like rest of things like they take the other half of the interval. And the second thing is second thing is the transition parameter can be obtained. How we are going to split the closed region and layer region with the help of transition parameter. The transition parameter is nothing but combination of the perturbation parameter and your number of mesh points. Okay, so this is my transition parameter. It is minimum of 1 by 2 or epsilon is epsilon log n. Epsilon is the perturbation parameter value, and n is the n is the number of base point that we are considering the problem. Okay, so like obviously your epsilon is nothing but without the boundary layer. So if it is without the boundary layer, I can able to say like the transition when we have the boundary layer only in this interval. Okay, yes. So that is the way like 16 used to find the transition parameter to split the regular boundary into boundary region and non-layer region. Okay. It's like these are like other numerical because we have the problem. So I have a solution. So like typically I just introduce only the boundary nature. It depends upon the problem. So can you keep silent for a few minutes? So like assume that like my problem is a problem something like this. I can say like the epsilon is in this state, u to 1 and u equal to 1. And your A versus 0 I can assume it is a general case I can consider. In such case, your B versus greater than 0, I have the two layers in both endpoints. We have like endpoints, right? Starting point, endpoint. In both endpoints, we are going to have the boundary layer. Okay, I'll show you the picture a little bit like more interesting. So like these two are the boundary layers. See, like my solution start from here. There is a sudden changes in the small interval. You can able to feel here. In the small interval, in the starting point, the solution starts from here. In the small interval, there is a sudden changes. It came down like very it came down like very quickly in the small region, and then it was like very smooth. It was very smooth, and we have one more layer at the end of the boundary. So here after reaching this, it is like getting quickly increasing. Okay, that's why what we are interested is we will give like more base points in this small region, so that we will get like more points here. If you get like more points, we will get a smooth curve around this. Actually, the blue one is here, like we have blue one. The blue one is exact solution, and the black one is nothing but a numerical solution. Okay, since I have introduced like I think I have introduced like 120 points in this, So I can able to almost overlap my exact solution. Okay. So if you have like 120 points, just assume that like you can split into three. Okay. So here I have like n by 4 points. Like 128 by 4, I have the point and a half point. In this smooth region, from this point to this point, again I am going to consider like n by 2 points. And in this small region, I am going to consider like n by 4 points. Okay. In such a way, I can able to resolve my boundary layer. Okay. Similarly, I have like different cases like this. If this convection initial problem, either you will get left bound layer or right bound layer. Either only possible. So like it is left layer concept. So like within the layer, I can take like 1 by 22 point. After this, I have like 1 by 2 point. And here from here to here, I have like 1 by 2 point. Or always like on the bound layer, we take the other 1 by 2 point. Depends on the problem. Similarly, it is an interesting problem. It does not have a direct application for similar particular problem, but it's like just interest of the researchers because introduced there are like two particular parameters. One is multiplied with the highest derivative, that is epsilon. This highest derivative parameter multiplied by the other particular parameter mu here. Okay, that is different like this. So like here, the reactivity problem, the width of the line is root epsilon. The combination with the problem, the width of the line is epsilon. But in the case of two parameter problem, my width of the line is ratio of the reactivity parameter. Okay, I will show you. I will have a picture. Okay, so like it is a like we are again the two parameter problem, so we are like two boundary layers, but with this never same. Okay, so like there are two cases we have. One is epsilon mu square less than epsilon case. In the mu square epsilon less than case, is just act as the reaction differential problem. Okay, if it is reaction differential problem, then with this root epsilon. So that is the thing. Then it is only root epsilon, but it is another interesting case. If mu square greater than or equal to epsilon, we have two combinations based on the problem nature. One side we have like epsilon by mu, other side we have mu. The other case is reverse one. Which is positive, we have the reverse case. Okay. So this other way we will get other boundary layer. I can extend. Yeah, these are examples I have considered. Like I am just taking this due to like time. I have done the problem. This problem. This problem I have done like my coefficients with the boundary conditions. I solved the problem. I got like first order accuracy. These are like boundary layers. We don't have any layers here because it's very smooth. Very smooth. At the midpoint, like 0.5, we have the layer, and then it is smooth, and the endpoint we have the layer, and it is like error graph. It is a solution graph. It is error graph. Likewise, like I have done like 4 different problems. It's a 2 parameter problem. This is where I have discussed my domain. So like I have like four boundary layers. So that's why I made like this. The reason is we have a disconnected at the point 0 point. Okay. So that's why we have like two additional layers in this left and right or right side of the disconnected point. So now it's a second case. First case and second case. And then and not only the ODE, I have solved the PD problem also. The 3D problem I have considered is the discretization and these are like the transition parameter. I have considered. Yeah, so this is my experimental example. So this is my layer. So here I can able to see like there is a layer. In the middle also I have a layer, and end also I have a layer. So other direction we have. So different value I have considered. Like epsilon equal to minus 6, and equal to minus 2 or minus 4. So this is like other combination. Like here epsilon is this and mu is greater than. Such a case also will get the boundary layer like this. Just give it a solution. Yeah, so like with this, like I can start my application of like different problem. So I just give you like two problems. I think I don't have time. Like two will I'll start. The first one is until now we are trying to solve the problem is kind of differential problem by using a numerical method. Different kind of numerical method. We have tried by various research. Okay, like last 25 years. Okay. Now the thing is that we are moving to the trade is how we are going to use the computer to solve the problem. The thing is, like machine learning, like the artificial intelligence, by using neural networks, by using such a tools, we are able to solve the problem. There are like two problems for like solved by the by raising value professor. Like we are copying the person. We are like take up the problem and here we are starting a very basic problem, but we are able to solve the like complicated problem, like two problems, turning point or something like that. Okay, that is one open problem. And second open problem is we have fixed boundary conditions. It's fixed boundary conditions are fixed like integer like 0 to 1 something like 106. Now we are interested to solve the moving boundary conditions. It's like really interesting application. We can't say like there is a real application, but still when we use it with observe, we can use the problem. Is that this interest of the researcher, like they are trying to resolve the problem where these boundaries are moving. The second problem, and third one is completely different. It is like very real-time problem. It is a mass Cuban mass. Okay, so like until now we are trying to like bring the computer with the equipment to the to the aircraft mass and trying to see the environment in aircraft mass. Okay, like we are trying to bring the human for such a research, like they need to survey for some days, right? Like we may be aircraft mass, they need to survey for some days. Okay, that is necessary for us. Okay, so in such a case, like assume that there is a medical issue happen for such a crew members, like the people used to call it like crew members, the team of the spacemen who are going to Mars. Okay, there is a crew members like how if any medical issues happen, like in your crew members, how they are going to handle the situation. That is very important, right? So otherwise we'll lose the person. Okay, so it is a very careful and major. So like it is a research project we have done with the France. That's why this things out we need to explore the problem. Generally, what will happen? Like two members must have some basic knowledge about how to treat the incident. Only for basics. If you have like for example, if you take your example, like you are calling it they have fever, you go to medical. Instead of going to the hospital, you go to medical. You take the 2 or 3 paracetamol, you take the see that period. You can try to see like whether it is medical or otherwise you go to the doctor. Okay. So likewise, the two members are able to support their people. Their other two members, which may be for example, if I get like absorbent pain, so the absorbent pain happens like due to like many reasons. If it is after it may be like temporary of the body, it may be like any other reason also. Such a case, like it may be like simple case, they can able to rectify. They have some medicine, they have some gadgets also. They have some small tablets. They can able to follow even the absorbent pain. What they need to follow the instructions will be given to us. Okay. If the system is very serious, if they want to get the support from the experts on the air, if they want to get the doctor experts from support from the doctor experts on the air, we have the restrictions because the people on the Mars, like like what is research rate? It is like almost like 225 million kilometers from the air. Okay? If you pass the message from there, even the message follow the light speed. Even the message follows the light speed, it will take at least 24 minutes to reach there. So you got a media receiving the message like after 24 minutes, like if you have like any serious issue. Okay? So like in such a case, to overcome that time lag, how we are going to help the people. Even though they need to pass the information like every time period, and they need to do the replay also. Okay? So how to handle this like these very parameters like time delay and other parameters? How you are going to model the equation? It might be a so stochastic differential equation. How you are going to make a model of this physical problem and how you are going to support the people in such a non-stop project, it's a non-stop project, support the people. Okay, so like so that we are going to like let's say it is a challenging problem, we are going to solve it. So we are in the discussion, like if you are interested, you can able to think over it and you can able to solve it. If the idea also you can able to write to me, I'll do it to you. Okay. Yes, these are the problem we have. And yeah, after like us introduce, these are the people who are working with us. These are the team members. These are the team members. Uh, Yeah. So these are like scholars like Mahasi, Jafar, Sujana, Jyotika. These are the scholars. Like these people are working in three different areas. Like not working in the respiratory method. Like he's taking the like from biological model and solving the problem. Very numerical method. And Mahasi is working on the protocol analysis. Like along with the other collaborator, Thomas Louis is participating UK. Is my collaborator. As Sudhana and Jyotika are working on the waterway problem. Here, we just started. We are already having touch with the other experts like Sanjay Kumar Murthy and they are solving the problem. Yes, they just started. They are doing some coursework and basic studies on the problem. Yes, we will use they are able to tell us on how to like great pathway. And like other two are the BTech students. We still like in the VAB, we got a culture to do the research of the BTech student. So what they used to like the BTech students who are like interested after the subject, they used to approach the they will see the profile of the faculty, like where they are interested, they approach the faculty and they get the problem or they get some research problem, they try to solve the problem. Like we used to publish the paper also with the BTech students. Okay, so we have a good number of strong people and educated people to take up the research problem. I am expecting the same from you. So if you are not if you are going for some higher studies, like after your PG, you are like to do the research of PhD, like try to grab the subject from the basic and understand the geometric meaning of like each and every problem. Okay, don't just say of like solving the problem, don't study. If you are like really interested in the research, then certainly you're able to grow be future research. Okay, yes. And other research we have, yeah, these are like my team. So Mahasingh, Sujana, Jyotika is my their friend. We discuss for some lines for the birthday party. And yeah, and then yeah, yeah, these are Purikan is very much like that. Kennedy Trichy, and these are like other collaborative because of probably some papers in the singular potential problem. These are like other collaborators. And we take up like different kind of problem like this, like virtual element method, like collaborating with the IIT Madras professor like on N. Sundararajan and he's the postdoc fellow under the Sundararajan. We are like four members, Rafa and others who are working the virtual element problem. And Thomas Lee collaborator for their pattern analysis. Like they are like different disciplines. Not only the mathematics nowadays, like we are interested in the multidisciplinary research. Like if I say like if I take a single potential problem, I solve a problem, it does not have much interest in the industry or it does not have that direct application research problem. The thing is even like the government also motivating or other outside India, let's say like Japan and other developing country or developed country, they are doing the multidisciplinary research. It means that like I should do like my contribution like mathematical modeling. The other people will do like chemistry, like people will do the reaction of engineering people they will do like their own model. You take a model, you use the mathematical information, they do the experimental lab information, they do they get the paper and publish the paper. Multidisciplinary research like actually like foreigners used to take the directly the problem from the industry and like different department people used to like sit together and solve the problem. Okay, that is a kind of multidisciplinary research. That is a culture like established in our India also. Like IIT and IIT parents to like people are like doing such kind of research. Okay, so like try to explore, like try to share the knowledge with the other departments and find two problems and grab the solution of the problem. Okay? So that will be really interesting and meaningful for us. Yeah, this is like these are the reference I have cited throughout my discussion. Uh, yeah, so like now I can open on that discussion. If you have any question, you can type in. Yeah, please feel free to ask even if you didn't understand also. I won't feel that um, it's meaningless to. Yeah, I think that like you are able to answer. Yeah, I know you are in that level, but even if there is a silly question also you can ask. You enter the research also you can ask like how to approach, how to find the way, how to do the like these project, everything project. Because your HOD is asking me to motivate you to come out from the regular course studies and do this. Not necessarily speaking English, we have common language only. Okay, if you don't have any questions, thank you for your patience. I hope like I will attach you interest in some topic that I have covered. If you have any question and if you are able to talk in the call, if you want to talk to your customer, you can write a mail. Based on interest, maybe I can have them phone number. Thank you.